Okay, so I've done what might seem like a rather long-winded intro, but as I was chatting with people during the break, the discussion here with the Lippmann-Schwinger equation, which I've kept the final content. So this is so we've defined this operator here, which is essentially the T matrix, which you define from the S matrix. So it's the standard thing you do, modulo a stripping of the energy conserving delta function, and you can give a closed form answer for it, as I've said. And the point about it is that the origin of this is the retarded propagator, so it comes from the fact that you have to solve, even quantum mechanics, you have to solve it causally, and therefore its T is naturally defined as an analytic function in energies, of complex energies, with the physical value being the boundary value from the upper half complex plane. And you can give a closed form solution, and that closed form solution you can check respects a dispersion relation, which is essentially summarized here. So up to some energy independent term, which is like a subtraction term in the language of dispersion relations, you have poles and you have a continuum, and you have this standard, this 1 over E minus W is the kind of dispersion relation kind of form, and it's naturally built into this. Now, this is for any quantum mechanical system where the Hamiltonian H0 and the potential are time independent. But of course, quantum field theory is just quantum mechanics of fields. It's nothing different. So this automatically applies to quantum field theory, including relativistic quantum field theory. So it's definitely going to be the case that a relativistic quantum field theory will copy the analyticity of this non-relativistic discussion. And so we're going to move swiftly on to relativistic in a second, but just to illustrate that, suppose, let me think about just classical scattering of the Klein-Gordon equation. So imagine I take now this system. So you can imagine this, I don't know, it's an axion, it's an inflaton, it's a Higgs particle. Let's imagine that for whatever reason I don't particularly care about, the effective action for the system has an explicit coupling to some kind of effectively external potential which depends on space. Well, that's going to induce scattering. So this is the Klein-Gordon equation with a space-time dependent mass, which I can regard, this is now my kick or my perturbation, which generates the source. And so then in this system, the equation of motion can be put into that form. And again, this is now, we think of this as the source, and this is the homogeneous part. And so even classically what would I do? I'd construct the free Green's function. So this thing, translation invariant system, with retarded boundary conditions. So G retarded has a theta function. And usually write this as delta. Delta is related to the commutator, although it doesn't really matter for this classical discussion. What matters is just that there's a theta function which is encoding causality. And so the general solution of this, of course, is then whatever is your incoming homogeneous solution plus your scattered solution. And you see that structurally this has the same form as what we input into the Lippmann-Schwinger equation. And in fact, cutting a long story short, you know that fields, you can naturally split them up into, a general solution is going to be a solution of, even classically, we can write it as a sum of positive and negative frequency modes. And we can define an S matrix even classically by thinking about sending in a wave which has a definite momenta and looking at how that scatters. And if you compute the scattering, so I'll just write this down to sort of cut a long story short because I don't want to go into it too much, but if you compute the scattering amplitude, the T amplitude in this case, what you get is, so I'll write it like this. So actually I should write it, I'll write it with an F and an F star. So these are the incoming wave packets. Actually, sorry, scratch that. Plus integral d4 x integral d4 y fk prime star of x v of x, and then this is the full GR v of y fk of y, where you should think of this as the incoming wave packet, this as the outgoing wave packet, and this is the full retarded propagator, so not the solution of the homogeneous one, but the full one. Now, take my word for it that that's the S matrix. I don't have time to derive it for you, but that's just the S matrix for purely this classical problem of Klein-Gordon scattering with a space-time dependent mass. So that will induce some kind of scattering. You send in a wave packet with some function fk of y, fk of x, which you should think of as, say, a wave packet supported around some momenta k. This is the scattering amplitude. Now look at the structure here. Look at the structure of it in comparison to this. It's even got the sign, it's got the minus v, basically being sandwiched between two wave packets. And then it's got the plus v times something which has the form of the retarded propagator for the full Hamiltonian times v. So plus v times the retarded propagator for the full solution of the Klein-Gordon equation times v. Okay? So that's the Lippmann-Schwinger equation in the relativistic context. Just classical scalar theory. So a simple generalization, we'll be looking at gravitational waves scattering in some theory where you've got, say, modified kinetic term and modified interactions. When you look at scattering there, you'll get a similar kind of equation to this, which will be just a Lippmann-Schwinger type equation with the full retarded propagator here. So that's showing you very clearly that the relativistic systems, if you phrase them the right way, just look exactly like this, and therefore they will have the prescribed analytic structure. Let me make one, so let me make another comment before I get onto the fully modern stuff, and that's that. So somebody asked me, so why aren't we using the Feynman propagator or something like that? And the reason is, even in quantum field theory, you should still always use the retarded propagator when you're solving the Heisenberg equations of motion. So if you remember, the first thing you learn about in field theory is how to compute time-ordered expectation values of Heisenberg operators. And those Heisenberg operators satisfy the Heisenberg equations of motion. If you just directly try to solve the Heisenberg equation of motion, you have to solve them in a causal way. So for example, if I take lambda phi to the 4, and I'll put in some mass renormalizations and wave function renormalizations, and do it in dim reg. Right, if I take that kind of system, then the operator equations of motion, which are the Heisenberg ones, are, because the system only has a potential as an interaction, it's basically that is equal to z lambda u to the epsilon lambda phi hat to the 4 over 3 factorial, give or take signs. I think I got that right. And you can rearrange this equation as follows. So if I define, if I write it as divided by z phi, and then use the fact that the asymptotic states would come with the actual physical mass, which is set by the pole in the 2-point function, then what will sit on the right-hand side is z lambda over z phi u to the epsilon lambda phi to the 4 over 3 factorial plus zm over z phi minus 1 m squared phi squared. And the right way to solve the Heisenberg equation of motion, specifically to talk about scattering, is to account the fact that because the mass gets quantum corrections, we should really reorganize this with the physical mass sitting here. And then this is all the interactions now, which is what I'd call J, now as an operator. So the formal solution to lambda phi to the 4 theory, in the same spirit as everything else we've done, is you take the ingoing free operator and you take the retarded propagator associated with the physical mass, and then you have j of y integral d4y. And of course this is a complicated operator and it includes all the renormalization constants in it and so on. But nevertheless, when you solve the operator equations of motion, you choose the retarded propagator. You do not use Feynman. Yep. Oh, thank you, yes. That was, I did the 3 factorial, but then I forgot the 3. So thank you, phi cubed. So when you solve the Heisenberg equation of motion, because they are the quantum analog of the classical equations of motion, they encode causality, and you should use the retarded propagator. Now, on this note, one other last quick comment thrown in, which is that you will all have learned in school the LSZ formula. So the LSZ comes in many different disguises, but probably the one you've learned is something to the effect, say, if I want to look at 2-2 scattering, then if I write it in position space, I have, I'm going to do this in real space, position space. I'm going to have 4 integrals. And then you have minus box x1 plus m squared through to minus box x4 plus m squared. This is really m squared physical as well because it's supposed to project onto the physical poles. In general, there's a wave function renormalization, but let's forget about that. And then you have exponentials. So the outgoing ones come oppositely to the ingoing ones. I've probably got the sign convention on this wrong. But you know the idea at least. So the ingoing and outgoing come with opposite signs. And then the punchline is that what you have is the vacuum expectation value of the time-ordered product of the 4 fields. That's what you learn in undergrad, not in undergrad. We may do. That's what you normally learn in a QFT class. And at the end of the day, this is all evaluated in the limit in which all the k-squareds go on shell. So that's important. So it's the on-shell value of the projected residue, the residue of the multiple poles of the time-ordered correlation function. So in the case of a 2-2 scattering, it would be the 4-point function that you do that. Well, it turns out, not hard to show, that because you're taking the on-shell limit at the end, you can actually replace this time-ordered product with the retarded product. And in fact, this is historically the order it was derived. It was derived first in terms of retarded products, and then as time-ordered afterwards. And then everybody forgot about the retarded formula. Now I should tell you, what do I mean by retarded product? And that is as follows. So you all know what a time-ordered product is, so I'm not going to explain that. I can define, for a retarded product, I'm going to use this notation here. So if I have a special point x, colon, x1 through to xn, I define the retarded product of operators by taking the operator and then taking the time-ordered with the exponential with sources, like this, and then doing the anti-time ordered, which will be very familiar to those of you who know about the in or Schwinger-Keldysh formalism. You take the anti-time ordered combination on the left, and then you, as you do with the generating functional, I didn't leave myself enough space, you sorry. You differentiate this n times with respect to the sources. And then at the end of the calculation, you set j equals 0. Now that defines an object called the retarded correlation functions, generalized to endpoints. It is essentially an in or Schwinger-Keldysh-like quantity, because you could think of this as just the, the object in the brackets as just the in expectation value of phi when I put in an external source with the classic time ordering, anti-time ordering. It becomes more illuminating if you write down some examples. So let me write you. So the first one is that if I just take R of x, that's just phi. So the retarded of one field is just itself. If I take the retarded of x and x1, it gives you theta x0 minus x01, phi x1, the commutator, which this is the commutator. The commutator times the theta function is exactly the operator analog of the retarded propagator up to an I convention. Why? Because this vanishes outside the light cone, and this imposes the time ordering so that it's only the future light cone that you get. And so this is the natural operator 2-point function. But you can go higher correlation functions. So if I go next up to the 3-point function, to cut a long story short, you get x0 minus x01, theta x01 minus x02, and then a nested sequence of commutators. And then there's the reverse order of that. So this is nested commutator. So it's a commutator of the field of the point x with x2, and then the commutator of that with x1, nested commutators. For those of you who've read Weinberg's paper on the in formalism and the nested commutators you get when you expand out the Hamiltonian interactions, that's just exactly this object. So these are, in fact, the natural definition of the causal in quantum field theory of the retarded propagator realized on different numbers of powers of fields. And they satisfy the property that all these things are 0 unless x lies in the future of all the other points. So they encode causality in that very clear sense. So you can see this very explicitly here. This thing is only non-zero if x0 is in the future of x1 and x1 is in the future of x2. Hence x0 is in the future of x2. But the order could be the other way around, so it could be that x2 is in front of x1. That's fine, you can get a term from this. But in any case, x0 is always in the future of everybody. So x0 is in the future of every other point inside those. Those are the full retarded correlation functions, which are somewhat more involved in the time-ordered version because they're in or Schwinger-Keldysh-like. But the S matrix can actually be written in terms of them. So more precisely, I can choose one of them and then write the other ones out. The reason it's the same is because the difference between the retarded and Feynman are Whiteman functions, things where you don't have any ordering, and they vanish when you go on shell, right? Because of the equations of motion. So it's the on-shellness that makes it that this is you can take the retarded stuff there. So I'm almost there. So last point then, there's another form which is even more useful. So this is describing a 2-2 scattering amplitude. 1, 2 goes to 3, 4. That's the LSZ formula. Actually, I've corrected it. I've gone back to pre-LSZ where it's the retarded propagator. But in terms of thinking about dispersion relations, there's another form which is very useful. And this is the following one. So it's also, I think you can find this in the LSZ paper, or at least papers of authors around that time. And this is the one that's really useful. So you can single out two of the particles, let's say 2 and 4, and do the integrals over them. We'll have the associated on-shell projections for x2 and x4. But 1 and 3, you keep as they are. So this is another, less familiar, but another version of the S matrix for 2-2 scattering. So it separates out the discussion for 2 and 4 and 1 and 3. So essentially, this thing, of course, is exactly theta x4 0 minus x2 0 times the commutator. So we're taking that operator, which is the 2-point operator analog of the retarded propagator that we've used up to now. And we're computing its expectation value between the 1 and 3 states. And this thing, of course, satisfies relativistic causality. So it's only non-zero if x4 lies in the future light cone of x1, which is just relativistic causality. So we can write the 2-2 scattering matrix. We can use this 4-point formula, which is the one, or the LSZ one. We can use that, But the LSZ one is actually not great for thinking about causality because it writes things in terms of time-ordered products, and time-ordered products are not causal. What's causal are retarded propagators or Schwinger-Keldysh in type things. There's actually, it's a bit surprising and somewhat forgotten, that you can naturally write the S matrix in terms of Schwinger-Keldysh type objects, and this is exactly what you've got here. And in fact, it was from this kind of form that the people in the 1950s, I guess, or early 1960s, so in particular Bogolyubov and Omnes and lots of other people derived dispersion relations for the 2-2 scattering amplitude. Now the point is that these are fully relativistic. So they do not encode, so the causality in this relation is what you sometimes call primitive causality. It's simply the vanishing of the propagator if t is less than t prime. So that's primitive causality. But relativistic causality is a much stronger condition because it requires vanishing only in the future light cone. So relativistic causality is primitive causality is this, right? That it vanishes here, but it can be non-zero up there. Relativistic causality is a much sharper statement. So what these people, and specifically Bogolyubov, it's in his textbook, Bogolyubov-Shirkov, that's what all Russians used to learn quantum field theory from, derived a dispersion relation for the 2-2 scattering amplitude from this formula because it encodes causality very clearly. And the punchline of that, so now we get to the point which was the base. So this became the basis of the 1960s S matrix program, and that is what has recently come to life again. And so now I'm just going to give you the punchline, but just tell you that it does come from that. So the punchline, so in modern parlance, we tend to work with Mandelstam variables. So we would define S is minus K1 plus K2 squared, and T is minus K1 minus K3 squared, or K2 minus K4 squared. And then for massive particle U, the third one ends up being 4m squared minus T minus S. So those are the normal Mandelstams for scattering. So I've got K1, K2 going in, and then K3, K4 going out. Something happens in the middle. And what follows from this statement is that the scattering amplitude which I like to use A for, but I know it's often used with an M. I think amplitude starts with an A. Some people think it starts with an M. But that's the amplitude with the momenta conserving delta function strip, so it's the normal thing. So you define S is 1 plus IT, and then you strip from T the momenta conserving delta function, 2 pi to the 4 delta for K1 plus K2 minus K3 minus K4. And then that's what I'm calling the amplitude there. So the statement is that scattering amplitude, AS of T, is for real T in some region. So if I'm scattering massive particles, so roughly speaking it's this region. We can get into details about the precise region. It depends somewhat on context. But roughly speaking, in the region of real T, so T is the momenta transfer, real T between minus 4m squared and plus 4m squared, roughly speaking. In specific context, it slightly adjusts, but there's a gap there anyway in T, which sits around T equals 0 and goes up to the mass. That A S of T is an analytic function of S modulo where it's not analytic. Poles and branch cuts. Now that's a trivial statement, but of course the content of the statement is where do the poles and branch cuts sit. That's really what matters. And what determines where the poles and branch cuts sit, where they sit, I read a story actually that so Schwinger was very bad at finishing off papers. He would be working on them for a long time. And Lippmann got so annoyed at some point he took Schwinger by the neck and held him up and said, "You have to finish that paper now." Anyway, that's that. So I'm going to get rid of Lippmann Schwinger. So what matters is the analytics, is where are the poles and branch cuts in S. So remember, S, of course, is the center of mass energy. And for that, it's just best to draw a picture. So this is now the complex S-plane. And the answer is, so typically, there is a pole associated with the physical particle. That's really the physical mass, not the renormalized mass or the bare mass. It's the actual physical mass of the particle. This is 4 times the physical mass of the particle. I'll drop the physical from now on, but you understand it's important to distinguish. So this is also the physical mass, because these are physical things. The actual pole in the Cullen-Lehman spectral representation. And there is discontinuity that goes this way. That's a branch cut. And because, so a typical, say if we're doing scattering for scalars, it satisfies crossing symmetry. So you always get crossing symmetry. For spinning particles, a little bit more complicated. But for scalars, crossing is the statement, the scattering amplitude as a function of S and T. And U is not really independent, so I don't really need to write it down because U is fixed by this relation. Right? So it's not an independent thing. That this is invariant under crossing, so if I switch any of the Mandelstam variables, it's the same thing. That's for scalars, just for simplicity. And because of that, because U is equal to 4m squared physical minus T minus S, and because of crossing, everything that happens in S happens in U, which means it happens in 4m squared minus T minus S. And so what happens in the relative, and this is what makes the relativistic problem different than the non-relativistic, is that now we get image a reflected branch cut going this way and a reflected pole. So the position of the reflected pole is 3m squared physical minus T minus S, because that's just 4m squared minus m squared. And this thing starts at minus T. I'm assuming no bound states here. If there were bound states, then we get extra poles there. But in the sort of typical field theories where, let's say lambda phi to the 4 or something, we're not worried about bound states. What we have is a particle. It has asymptotic states. They have mass. It gets out to infinity. That shows up as a pole in scattering amplitudes. And then there's the branch cut, which is associated with quantum corrections. Why does it start at 4m squared? Because the first interesting thing we can write down is a one-loop diagram beyond tree level. And if you cut the loop, then the minimum energy of that across the cut is 2m. But in general, it's more than that, and it's a spectrum. It's a continuous spectrum more than that. And so that's why you get not poles, but a branch cut. So it's this aspect, this mirroring, which makes the relativistic scattering amplitude somewhat more complicated than the non-relativistic. Because if you remember, in the non-relativistic, you basically got in W, this is T of W, something like this, where these are just bound states, okay? But otherwise, it's the same. It's the same in the sense that all the discontinuities are on the real axis because they're associated with real physical things. Okay? The other sense in which it is the same is that just in the Lippmann-Schwinger equation, you can very easily compute the discontinuity across the branch cut by computing the imaginary part here, because the only thing that's complex is this. And you see that when you do that, what you get is something that's very obviously positive when evaluated. Well, let me state that for sure. This is where the positivity comes in. So in Lippmann-Schwinger, the imaginary part of T of E plus I epsilon, V is real, it's mission, so the only thing it comes from the W, so it comes from the imaginary part of V 1 over H minus E minus I epsilon V. Now this is obviously, it's a pi V delta H minus E V. So if we sandwich that between the same state, so let's say psi, so if we look at elastic scattering, we take the same initial and final state, then you see that this is it's an on-shell projected version of the square of something, but because it's the square, it's clearly positive. That's coming from unitarity. So because of unitarity, the discontinuity across the branch cut in the Lippmann-Schwinger equation is manifestly positive because of unitarity. And the same thing is true here. The imaginary, or the strictly speaking discontinuity, but for a real scalar, I can say this. So this imaginary part, by which we mean imaginary, AS plus I epsilon for real T minus AS minus I epsilon for real T divided by 2I. And by S minus I epsilon, I really mean this value minus this value, which is obtained by analytically continuing round like that. That's what the discontinuity is. That is determined by unitarity, just like it is over here, and is manifestly positive. Okay, so let's put these things together. So the proof of that is quite hard, to be honest. But conceptually, it follows from the same logic that we proved, say, the Kramers-Kronig or the equivalent quantum mechanical one. So it's conceptually the same. It's just a lot harder in the relativistic case to plug it through. So if the scattering amplitude is an analytic function of S for fixed real T, then it means that I can write a dispersion relation. Or so if you like, I can use Cauchy's theorem to infer the value of the function anywhere away from the branch cuts and the poles by appropriately deforming the contour. So I can basically, so I'll draw it again. So modulo the poles, what I do is I take a contour which goes around here, like that, like a hamburger, the hamburger contour around the branch cuts. And everywhere it's analytic there, so if I do the integral of the scattering amplitude around that, you get 0 because it's analytic, modulo the poles if I subtract out the poles. But if I now take this scattering amplitude and divide by S at some particular value, it's a star, which itself can be complex, and I perform that contour integral around that contour, then by Cauchy's theorem, that's going to give me 2 pi I times the residue at that value, which means turning it around, I can infer the scattering amplitude at any point in the analytic region from this integral. Now this integral collapses into the contribution which is integrating around the branch cut and the contribution for it at infinity. Now let's suppose the contribution infinity is 0. I'll tell you how to correct that in a second. If we assume that there's no contribution from infinity, so I can take that the normal trick, I take the semicircle out to infinity and the scattering amplitude goes to 0 there, then modulo the poles here, everything comes from the branch cut. And you see the way the contour goes, of course you're integrating this way here and that way there. So what this picks up is the discontinuity, because if this was a continuous function, the integral that way and that way would just cancel against each other. So that entirely is determined by the discontinuity. So you have what's called the S-channel discontinuity, right? Because this is what comes from the physical scattering and thinking of S as the center of momentum transport. But then you have this mirror copy, which is because of the relativistic system, and this is called the U-channel discontinuity. So as I say, if I'm a little bit lazy, if I ignore the semicircles at infinity, then the punchline is that the scattering amplitude is determined by, well, now I should at least put the poles back in. So there's a pole here and a pole here. So I get, in principle, the residue can be a function of t. So I have the pole, which is this one. And then I have the mirror pole. Do I have a different color? I do have a different color. There we go. That's really looking like a hamburger now. So just because of, so if I write a dispersion relation of fixed t, fixed real t, I'm not making t complex. But S is complex, so U is complex, and crossing symmetry says that AST should equal AUT. So that means that whatever I have in S, I have in U as well, which means I have the mirror pole. So this is the red one. Should have written that in red. And then I have the blue one, which comes at m squared physical minus u. I could write u back in terms of S, but it's kind of nice to make it more symmetric by writing it with the u. And then the Cauchy theorem argument is what gives you what makes it a dispersion relation. And you have imaginary part of A. So now often people write this as S prime, and I'm going to correct this in a second, but let's go with that. So this is coming from the integral from 4m squared physical up to plus infinity. And then on the denominator, I have S prime minus S. And that's really the red one. So this is the S channel one. And then there's a mirror copy which goes from which also goes from 4m squared physical, written like this, S prime up to infinity. Now I prefer not to use S prime as the integration variable, because what is S? It's the center of mass energy. So where the discontinuity comes from is that when you scatter two things in, they create an intermediate state, and that intermediate state has some energy squared. So that intermediate this is really the S prime is really the energy squared of the intermediate state you've created. So in analogy to what you do in the Challen-Lehmann spectral representation, which is where you write the propagator, the Feynman propagator, say as 1 over up to minus i's, m squared physical minus k squared with a z factor plus integral over a spectral representation. So mu is essentially it's actually plus, isn't it? Plus k squared. So mu is essentially the mass squared of the intermediate state, the effective energy squared of the intermediate state. So I prefer to use, as was done in the 60s, mu as the integration variable to reflect the fact that we should really think of this discontinuity coming from the creating intermediate states of energy squared mu. Okay, so I'm still ignoring that, but just to recap, this just comes from analyticity, it comes from Cauchy's theorem, but the physics is encoded in where the singularities are. So the fact that you have, this is really the physical pole, this one here is the same as that one. It's the same pole that you get in the Challen-Lehmann, it's at the same mass. It has to be the same, otherwise the theory doesn't make any sense. That's the analog that's coming here. This piece here is the integral along the right-hand, the discontinuity with the right-hand branch cut. This is the exact analog of that. So in the Challen-Lehmann, this we call the spectral density. It's basically weighting how much the overlap of the field is, sandwiched between the vacuum and single particle states. Whereas in the amplitude, it's this quantity. However, just like rho is positive because of unitarity, this thing is positive. And it's actually positive in the region t between 0 and 4m squared. I'll tell you why in a second. So it has very much the same structure. And as I say, again, what makes the relativistic scattering problem different is that you get this image copies which come from the U-channel processes, and they get folded in. Certain amplitudes you don't get the U-channel, but not for, say, scalar scattering. You always get the U-channel processes. Okay. Yes? Mm-hmm. Is there a way to derive your representation here in the same way? Yes. So I did it here. So if I want a insert a complete set of states, energy eigenstates, that would collapse the delta function, and then I could write it explicitly. So that's the analog here. In the relativistic case, it's a little more work, but you're absolutely right. If I go back to this is a formula. In that, remember the retarded propagator was theta times a commutator. The commutator, when I took its expectation value, will collapse into two Weidmann functions. And so indeed, the imaginary part will be determined by the Weidmann functions, but now evaluated not in vacuum, but between two single particle states. So it's a bit more complicated, and that's why it's also t-dependent. Right? This is just a vacuum VEV. This is a single particle VEV on each side. But conceptually, the idea is exactly right. Yes. Yeah.
Using crossing symmetry principle, could we go further and then just state that we also have to have a pole in T here?
Very good. Now you're jumping ahead of me. The answer is no and yes. Okay, but let me come back to that. So let me stay with this. Because what I'm doing here is I'm writing, I should qualify, a dispersion relation in for fixed t, fixed real t. That's important. So S is complex, but T is not. So the SU symmetry is important. The ST symmetry is much more complicated. I'll come back to that point, but thank you for raising it. Now, the contribution from infinity, I need to deal with that. So for that, I note that. Okay, we can get rid of you now. For that, I note that where that comes from is the fact that the imaginary part of a mu of t may not go to 0 as mu goes to infinity. And if it doesn't, then this integral doesn't converge. However, you can derive, at least for massive scattering, there is a bound. So there's a bound at t equals 0, which is called the Poisson bound. And then there's a generalization that applies from 0 to 4m squared, which is called the Gin-Martin bound. And the Poisson bound basically says that the imaginary part of the scattering amplitude as a function of mu at t equals 0 is less than mu log mu squared. So it doesn't grow more than mu log mu squared, so it's just slightly above mu. And the Gin-Martin bound says that if you now make t positive up to 4m squared, it's less than mu squared. So scattering amplitude never grows as much as mu squared. And so for that, it's enough to do what's called a subtraction. And what the subtraction is basically saying, instead of trying to write a contour integral for this expression, I insert an extra s minus s0 at some subtraction point, and then that determines s star minus s0. So if the scattering amplitude grows at large values of s, I just divide it by some number of powers of s until it doesn't grow anymore, and then I run the argument again. And the punchline of that is that what it does, if I choose the subtraction point to be 0, what it does is it puts a power of mu here. And I guess to deal with two subtractions, I need a mu squared. And then this becomes s squared when you do that. And this is mu squared. And this becomes u squared. And then what you get left over is a polynomial, which is linear in S. Actually, if it's SU crossing symmetric, this piece vanishes, which I guess is what I've done. So in fact, I'll just write that for SU crossing symmetric. And I won't go into the steps for that, but that basically coming from that argument. And so this is the final form of the dispersion relation, which is used in essentially all modern treatments of S-matrix bootstrap and positivity bounds, etc., etc., etc. Now, if we focus on 4 dimensions for simplicity, not that we need to, then the scattering amplitude, so if I write t in terms of angles, that's this, and where theta is the scattering angle, I think I got that the right way around. Then there is the partial wave expansion. And this comes from the fact that when we're just doing 2-2 scattering in a system where we're not breaking rotational symmetry or full Poincare symmetry, then the S matrix will diagonalize into partial waves, which are just basically states of definite angular momenta. So in 4 dimensions, the partial wave expansion is the scattering amplitude up to some normalization is given by 2L plus 1, that's the standard Legendre type factor, and then the Legendre polynomials, which determine the t dependence, and then times these things, which are called the partial waves. So essentially all this is doing is a decomposition from plane wave states, plane wave scattering, into partial wave scattering. So the S matrix diagonalizes in partial waves, so it's really the more natural one. But we like to think about scattering in terms of plane waves, and that's just that decomposition between the two. So you can think of this effectively, so more precisely, the S matrix diagonalized onto a given partial wave is up to some normalization, some annoying relativistic normalization given by this partial wave amplitude. And unitarity unitarity is the statement that the modulus of SL is less than 1. So if it's equal to 1, we call it elastic scattering. What that means is that we're not creating any higher particle states. We're below the threshold to produce multi-particle states, and so the 2-2 scattering amplitude can be unitary on its own. But of course, in general, that's not true. So as we go to higher energies, we can create multi-particle states. And so in general, unitarity is the statement that the modulus of that is less than or equal to 1. Okay. So let me tell you how we do modern Bootstrap approaches, which is actually really just the 1960s Bootstrap approach, but it just works now because we can do it better. But it's all based into this. And let me give you the idea of how this works. So it works as follows. Well, there's many ways people do this, but I'll give you the way which is the most Kramers-Kronig-y. Well, actually, leave me. Yeah. So you see from the partial wave expansion that this is true in the physical region. This is true in the physical region, which is s bigger than 4m squared and t less than 0, so that there's a real angle there. So we can compute the imaginary part in the physical region. Remember, this is the discontinuity. Well, the Legendre polynomials are real, and L is real. So in fact, the imaginary part of the scattering amplitude in plane waves is just given by the imaginary part of the partial waves. Now those imaginary values of the partial waves, they're functions of S in the physical region, which is bigger than 4m squared. Sorry, that's not what I wanted to do. I want to see you. Okay, and so that is the input here on the right-hand side in this relation. So what we can do is we can make an ansatz for the imaginary part in the region, in the physical region. So just make something up for that. And if whatever that is we've made up, that determines what we think the imaginary part of the scattering amplitude is going to be. We can then take that answer and plug it back into this formula to recompute the scattering amplitude. So we can now write this, so modulo the annoying subtraction point and the poles, we can now substitute this directly into here. Where this S now becomes mu, and this is now the imaginary part of FL of mu. And that's divided by mu squared mu minus S. And then you add the S goes to U mirror, the crossing mirror. So in other words, given the imaginary part, given an ansatz for the imaginary part, we can directly compute this integral now, which is guaranteed to be convergent, because as long as we've satisfied the Froissart and the Gin-Martin bounds, we know that mu squared here is enough to make this integral convergent, so that's dealt with our number of subtractions. And so we can actually calculate this, which means we can then go back and compute the real part, because this gives you the full scattering amplitude. So as in Kramers-Kronig, if you know the imaginary part of the refractive index, you can compute the real part. If you know the real part, you can compute the imaginary part. No one would do it that way. So one interesting way is give the imaginary part, you can compute the real part. So we can get it directly from this. So modulo these bits, which aren't super important, we can directly compute the real part of the scattering amplitude, by which we mean the real part of the partial waves. And so that's equal to, where does the real part come from? Well, what is complex? So this is real. That's real, that's real. So the only place where there's a question about what the real part is the fact that this is S. Now remember that the physical scattering amplitude is the boundary value from the upper half complex plane. In this case, it's the S complex plane. So what we really mean is this S, the physical S, has a little I epsilon there, and the same for the U. It's the I epsilon goes the other way. So what the real part does is it's evaluating the principal part of that, right? Because the imaginary part gives you the delta function, and the real part gives you the principal part. So this then gives S squared over pi d mu 4m squared to infinity and blah blah. 16 pi. Yeah, this is a bit boring to write this out, but let me just do it for sake of completeness. Imaginary FL of mu. And then, rather than writing that, this is then the so the mu squared can go along. And then this is the principal part of 1 over mu minus s minus I epsilon, plus s switch to u. Now, just to remind you what the principal part is, it's when you take this symmetric average over the I epsilon. So the principal part of 1 over x plus I epsilon is a half 1 over x plus I epsilon plus 1 over x minus I epsilon, which is basically x over x squared plus epsilon squared. So essentially it's 1 over x everywhere except x equals 0, and it cuts out the x equals 0 pole to make sense of it. So just like Kramers-Kronig, we can make an ansatz for the imaginary part, use the dispersion relation to compute the real part. Okay? So what? So now the way you can do this, because this formula is true for any t between 0 and 4m squared, actually it's true for negative t as well, but it's more, oh, yeah. It's true for any t in this region. The way you do it in practice is you say, of course I can't make an ansatz for all L equals infinity modes, that's going to be too hard work. Let's suppose I truncate the partial wave sum at 100 partial waves. So I've got 100 values of the imaginary part. Well, I can take this relation and evaluate it at 100 values of t, and that gives me then a linear equation, which is basically a 100 by 100 matrix, from which I can infer the real part of the partial waves. So there's 100 values of the real part of the partial waves from the 100 values of the imaginary part of the partial waves by evaluating at 100 values of t. Now when I've done that, then I go up to here and I say, well, that's all very well and good. If I satisfy the dispersion relation, I've satisfied causality. That's not good enough. I also need to satisfy unitarity. And so what you then do is you take your imaginary part, you take the real part you've computed, and you check, is the modulus of SL, which is obviously built out of the real and imaginary with this particular normalization, is it less than 1? And if it is, it's good. And if it's not, it's bad. You try again. You change your ansatz. And so this creates just a numerical scheme, which I know works because we've done it. I didn't do it because I can't do anything numerical, but my collaborators have done it anyway. So this is a particular example of a Bootstrap scheme that it's very easy to run numerically because you just make ansatzes for this. You make intelligent physics choices. But the rest is just very pedestrian. You compute the real part, you check, is it unitary? If it is, good, you keep it. If it's not, you throw it away. And you iterate that procedure until you can construct, and this is the true Bootstrap in the 1960s sense, you construct the full scattering amplitude, as many partial waves as you want, guaranteed to be unitary, guaranteed to be crossing symmetric because it sits in this dispersion relation, and guaranteed to be causal because it comes from the dispersion relation. Now, there's one extra point I should say. So people do other methods. That was just one particular method, but I think it's the one that's most physical in the sense it's really what Kramers and Kronig would have done if they were thinking about it. That's quite an extrapolation, but so one other thing we have, of course, is that what we wrote down, that dispersion relation we wrote down, had manifest SU crossing symmetry. But, for example, ST crossing symmetry is completely hidden. So one way to do it is just to force it. So demand that AST is equal to ATS. And in practice, you force this at the level of the dispersion relations. You can just equate the dispersion relation. So I can equate A of t plus the pole pieces plus 1 over pi integral d mu imaginary A mu t over, and then this is mu squared, mu minus s squared, plus u squared over pi integral d mu imaginary part of A mu t divided by mu squared mu minus u. And you demand that that's equal to A of s plus the equivalent pole pieces plus t squared over pi integral d mu imaginary part of A mu s u squared mu minus s. No, t. Beg your pardon. And then u stays the same, so this is u squared integral d mu imaginary A mu s over mu squared u minus u. And doing that basically imposes constraints on those partial waves. So, because if you look at this equation, what is in this equation now? It's just the imaginary parts, right? It's just some integral of the imaginary parts in this particular combination is equal to integral of the imaginary parts in this particular combination up to these pieces, which don't play a huge role in that discussion. And so what that gives are there's constraints on the imaginary parts which must be satisfied in order that full crossing symmetry is satisfied. And these constraints, the constraints that follow from these, that leads to constraints which are now referred to as null constraints. So the constraints on the imaginary parts necessary so that it exhibits full crossing symmetry. So those are very non-trivial implicit constraints because of the structure of them. Now, I suspect I'm running out of time, right? How long have I got? Who's in charge?
19.
Oh, you. 19 minutes. Oh, pardon?
19.
19. Okay. That's better than I thought. Good. Good. Okay. So let me just give you an example of these constraints. So up to, I'm going to get the normalizations wrong on this, but roughly speaking, the leading form of this constraint in d dimensions is as an integral, and then there's some L-dependent coefficient. There's an integral over mu to the 5, and then the imaginary part of the partial wave. And then what you get is a polynomial in L. And I wrote it down, but I can't read my own. D minus 3. It doesn't matter precisely what it is, other than that it's polynomial. And that has to be 0. So where you get that from is you take this relation and you expand in powers of s on both sides. Usually do this in a theory of the gap. So this starts at m squared m physical, but usually do it in a theory of the gap. But anyway, it's still true even in the theory. Well, as long as there's a gap, then you can expand on both sides because it's analytic there, and you match up the terms on both sides, and you always get some polynomial in L averaged over the partial waves has to be 0. Now the typical structure of that, so if we just focus on this for, say, d equals 3, what you get for d equals 3, just to simplify the algebra, what you get is basically that the average in this particular weighting, so we'll weight using the imaginary part of the partial waves as the weighting, the average of L to the 4 is equal to 11 over 2 times the average of L squared. Now, it doesn't matter the precise numbers here, but conceptually you get something similar like that for general dimensions and as you go to higher orders. So what happens is that higher order polynomials in L, or higher powers of L, are constrained in terms of lower order ones. And if you think about this for a second, what this clearly tells you is that you can't have arbitrarily large support at arbitrarily large L, right? Because L cannot have support for arbitrarily large values. Because according to this particular measure, the average of L to the 4 has to be equal to 11 over 2 the average of L squared. So clearly L can't be arbitrarily large, right? So if you make L too big, L to the 4 is always going to dominate over L squared. So the null constraints, what they do, which you don't get from the fixed T dispersion relation, is that they cut off the power, or they cut off the discontinuity, they cut off the imaginary part at large L for a given S, we should say, or given energy scale. Yeah, sorry.
How am I supposed to read this equation? Because the L, does it interact with the mu?
This is a function of mu. So mu is, remember, is the energy squared.
But for me, this seems like we have...
Oh, sorry, I missed a bit. That's why. This is sum. Beg your pardon. So it's an average. It's an average sense. Yeah, sorry. So roughly speaking, it's saying the average of L to the 4 is bounded by the average of L squared, which means that you can't have arbitrarily large values of L, and that's the consequence of the constraints. So this combination of things, and that's basically it. What is it? Let me reiterate. It's causality in the form of a dispersion relation. It's unitarity here realized at the partial wave level on each partial wave. And it's crossing symmetry being imposed back in. And you put those things together, what you find is that those imaginary parts, and real parts by extension, are strongly constrained, much more strongly than we might have imagined from the outset. But they're strongly constrained in such a way that the resulting scattering amplitude is also even more strongly constrained. What do I mean by that? So, so I hope even if you don't get all the details, you at least get the sense of the way it's working. So let's. So in those integrals, which are integrals over intermediate states, I put that the lower limit of the integral is 4m squared physical. And the reason is that because we're scattering some particles of mass m physical. And so just a one loop diagram will generate that contribution. However, remember that we also, what we haven't mentioned so far is that this is all sort of 1960s, but what we haven't mentioned so far is that we should also imagine that what we're scattering is some fields, and usually we're doing a calculation in an effective field theory, because everything is effective field theory unless it's the actual UV amplitude, in which those, say, string amplitudes or something. So typically, most of the time we're working with an effective field theory, which is a theory defined up to some energy scale, which is the cutoff. Now, the point about this diagram here is what's running around the loop are the light particles, by which I mean, so if I define a light particle as a particle in the low energy effective field theory, whereas a heavy particle is something that's part of the UV completion, but is not in the effective field theory. This particular process, which leads to the branch cut at 4m squared, is part of the low energy effective theory, which means we can calculate it within the low energy effective theory. If you give me a low energy effective theory, I can calculate that diagram for you. So because I can calculate it, I can figure out what its contribution is, this integral, and subtract it off and get rid of it. So you can always calculate, you can use the low energy effective theory to calculate the imaginary part in the region you trust the low energy effective theory, which is below the cutoff squared and then above 4m squared physical. Okay? So whatever theory it is, some weird inflation model, Galilean theory, gravity, whatever it is, I can do that computation, which means I can subtract out that. If I know what its value is, I can just subtract it out, and then focus on the rest of the integral, which is the unknown part. So the unknown, which is part of the UV completion, is the part of the integral that goes from lambda squared up to infinity. Okay? So let me say that again in a different form. Ow! That hurt. So let me say that again. So the statement is, this is where we can put all this stuff as bounds on effective field theories. So the statement is that the amplitude we've been talking about so far is the amplitude, by which I mean it's the amplitude of the full UV complete theory, right? Because I didn't tell you what the theory was. I just said it's an amplitude satisfying all the requirements, and so it can be applied to the full theory. So it's that object which satisfies this dispersion relation. Plus s goes to u on that one, and then plus s squared over pi integral d mu from 4m squared physical to infinity, the imaginary part of a mu over mu squared mu minus s plus s goes to u. And what we can do is we can take that amplitude, that full amplitude, and separate out, write it as the truly IR part, or the EFT contribution, which comes from, well, I'll tell you what it comes from in a second, plus then the genuine UV part. By UV, I mean above the cutoff of the effective theory. So what is the EFT part? Well, it's anything that can be computed within the EFT. Well, this part can very easily be computed in the EFT, because this is a function of t, which is supposed to be at small t. It's independent of s, which means I can compute that in the EFT. This is a pole that sits at the physical mass. That's the mass of a particle in the EFT, and therefore, by definition, that should be computable within the EFT. If it's not, the cutoff of the EFT is below the mass of the particle. So we have to be able to compute that within the EFT. And then, as I said, although we clearly can't compute the full integral in the EFT, we can certainly compute the low energy part of it. Up to the cutoff of the EFT. Okay? Does everyone get what I'm saying now? Okay, so then this is what we really care about. That's the remaining UV part. And that comes entirely from the branch cuts from lambda squared up. And that, of course, is the part we don't know. We don't know anything We can't compute it, that's for sure, unless we know our UV completion. But what we do know is that it has to take this form from the dispersion relation. It has to take this form where there's the imaginary part, which is positive, and has a dispersion relation. Has a partial wave expansion. That's what I meant to say. Where these are positive in the physical region. We know that much. And because that's positive, you can see very easily now if I take this expression and I start Taylor expanding in S, so don't worry too much about that S squared sitting out front, because 1 over mu minus S, its expansion is 1 over mu plus S over mu squared plus S squared over mu cubed, You get that from that expression. Of course, you also get the expansion of 1 over the U-channel contribution. And what happens when you Taylor expand this, and that Taylor expansion is a good one because it has a regime of convergence set by lambda squared, because that's the beginning of the branch cut now. Let me make that clear. That UV part of the scattering amplitude, it has no poles because we removed them. Its analytic structure complex X is now this, it comes from the cutoff here, and then this is technically it's 4m squared minus the cutoff minus t down here going that way. But now there's this huge region of analyticity where we can Taylor expand that, and that's a good expansion because we've removed those low energy discontinuities calculated within the EFT. And that expansion is captured by this. Now S plus U is equal to 4m squared, so because U is not independent of S, this is not interesting by itself. But what you notice is that each term, when you look at the even terms, each term in this expansion is positive. These are positive for positive t. These terms are positive. This is positive. Everything in that expansion is positive. And so you get that those coefficients you get from that expansion, trivializing ever so slightly, but are basically guaranteed to be positive when you expand them out. Now, what is this AUV? What it is basically the tree-level scattering amplitudes of the Wilsonian effective action. With the poles removed. Now, why is that? Because we think what you do when you compute a Wilsonian effective action is you're integrating out all the physics at high energies down to some cutoff scale, but you're not yet integrating out the low energy physics and the loops of that. So if I take this Wilsonian effective action and I compute the tree-level scattering amplitudes of that, those tree-level scattering amplitudes do not include light loops explicitly because you're only computing to tree level, but they do implicitly include loops of the heavy particles that you integrated out to get that Wilsonian effective action. So roughly speaking, I'm trivializing ever so slightly, but that's basically the idea. The Wilsonian effective action, which is the effective action you write when you write your paper, equation number 1, what is that action? It's the Wilsonian effective action, right? That action, its tree-level amplitudes are what are computing this. So what we're getting is that when we take the scattering amplitude you get from computing the tree-level Wilsonian effective action, and you expand it out in powers of energy, you're going to get lots of things that are positive from doing that expansion. And it's a bit more than that because you have the crossing, the null constraints, and so on and so on and so on. So if you put all this together, what you get is, so in a theory which is fully crossing symmetric, so if I look at scattering of scalars, I can always package together scattering amplitudes in terms of two crossing symmetric variables. So one is s squared plus t squared plus u squared, or equivalently st plus tu plus su. They're more or less the same thing. And the other one is stu. So this is these are the two crossing symmetric variables from which every 2-2 scattering amplitude, which is manifestly crossing symmetric under triple crossing symmetry, can be built out of. It's something of order energy to the 4 and something of order to the energy to the 6. And if you do calculations, you do one loop and lambda phi to the 4, you'll find you can write the answer in terms of that. Then, as I say, if you just look at the UV part, which is essentially what you get from the Wilsonian effective action, ignoring the light poles, then that will have an expansion in energies which in 4 dimensions on dimensional grounds will go like x over the cutoff to 4. That will be the first term. Y over cutoff to the 6. X squared over cutoff to the 8. The next term is xy, which is over cutoff to the 10, etc., etc. So this is just some particular parameterization. But what the parameterization is reflecting is that in 4 dimensions, the scattering amplitude is dimensionless, right? Because in lambda phi to the 4, it's just minus lambda at leading order, so lambda is dimensionless in 4 dimensions. So scattering amplitude is dimensionless. X has energy dimensions of 4. So however this comes in dimensionfully, it must be set by the lowest dimensionful scale in the problem, and which of course is by definition is the cutoff. Ow, I'll do this again. Because this is setting the regime of convergence of the expansion, right? So it's guaranteed that's the scale. You don't, wherever the discontinuity kicks in, that's the scale that's going to come in. It's not a tuning. I'm not making it up. It's by definition of the analytic structure that that's the scale going to set the expansion parameter. So once you've phrased it like that, which is that this is not a naturalness argument, but it's the expansion natural from the analytic structure, assuming the branch cut begins at lambda, we naturally get a set of dimensionless coefficients here. So G2, G3, etc., etc., they're all dimensionless. And these are the objects that pick up these positivity constraints coming from the positivity of the imaginary part, the unitarity, the null constraints, etc., etc. And so the leading such constraint, the first one you get, in fact, is just that G2 is positive. And that directly comes from this piece. So because this already goes like s squared, and then there'll be an equivalent u squared, and then if you do this subtraction in a crossing symmetric way, there'll be a t squared. So the piece that goes like 1 over mu here from that times s squared plus u squared plus the equivalent t squared will repackage into this x term and give you that G2. And you see that that G2 has to be positive, as I say, because everything over there is positive. The Legendre polynomials happen to be positive for positive t, or particularly they're positive for t equals 0. The imaginary parts are positive, etc., etc. So that has to be positive. Now, as you go higher up, you don't get clean positivity. It gets a little bit more subtle than that. But what you get is bounds on the coefficients. This is where I'm going to draw a picture. So roughly speaking, the natural objects are G3, I'm going to normalize to G2 to the 3 over 2. So G2 is positive, so that sets a normalization. We could basically, it's roughly 1, because it ends up being, in practice examples, it ends up being roughly 1. So you get G3 on normalized by G2 on one axis, and G4 normalized by G2 squared on the other axis. And so when you impose these full unitarity, bootstrap, crossing symmetry, null constraints, bounds. You stick them all together and you just numerically check, am I satisfying unitarity, am I satisfying crossing, dispersion, etc., that you infer from these relations. What you get is a compact island, which roughly speaking looks a bit like this, in which the remarkable thing is that these numbers, and I'm not being very precise about it, so it doesn't matter too much, but the range of the numbers over which are all sort of order 1-ish. So maybe there's a factor of 10, depending on how you choose to normalize things and so on, but roughly speaking, they're all order 1-ish. So this is what follows from imposing all of these constraints. So the positivity of the imaginary part, the real part being positive, from that, and therefore, in fact, full unitarity, the crossing symmetry, etc., you put all of this information together, and you find that the coefficients here end up being bounded in a very clear way. This one is always just positive, that's it. But once that is fixed, the other ones, in terms of it, end up not only being bound, not necessarily positive, but they're not only having bounds from above, but also bounds from below, which puts them into compact islands. So this is something that's really only sort of in the last 10 years been put together. And this is tremendous progress from the perspective of our thinking about effective field theories. Because we used to just use sort of crappy naturalness arguments, where we would write down a Lagrangian and parameterize things, and we'd say, well, naturalness suggests that all those terms in the effective field theory expansion might be of the same order. Here, naturalness is justified by dispersion relations whose origin is causality, which is mind-blowing if you think about it. So now what are these things? Well, this is, as I say, this is just a scattering out. You should think of this as the tree-level scattering amplitude of some Wilsonian effective theory, because we're not including light loops, and I've dropped the light poles. So there's no light stuff, but there is the heavy stuff. And roughly speaking, in terms of interactions, for those of you that don't live in the 1960s and like Lagrangians, then G2, this G2x term corresponds to the famous d phi to the 4 interaction. Up to an appropriate sign that's the right one for it to be positive. I'm not going to get that right now. G3 corresponds to interactions that look like d phi squared d mu d nu phi squared, the famous Galilean type. Well, not exactly a Galilean, but it's the kind of things you get in a Galilean, if you know what that is. And then the next one, G4, the next one, G4, is basically d mu d nu phi squared squared, and so on and so on. Essentially, there's a unique, well, no, so it's not unique, I shouldn't say that. So there's a collection of, because of field redefinitions, it's not completely unique, but up to field redefinitions, you can attach a local Lagrangian of the kind that we get in weird effective field theories, or we generate in effective field theories, associated with every one of these things. And again, what's happening is that these dispersion relations, through the combination of causality, unitarity, crossing symmetry, are fixing these coefficients, which are specifically the coefficients in the Wilsonian effective action. So that's the action you write down as the first equation in your paper, right? Those coefficients are getting constrained because of these relationships. Yeah, that's a great place to stop. Okay, thank you.